I don't believe these slides were included in the USB because I didn't give them to anyone. So my punishment is providing you all my beautiful email, ashook@gopivotal.com. Feel free to email me, and I'll put them up on Dropbox or something and share them all with you. Or if you have any other Hadoop-related questions, please feel free to send me an email. I'm usually pretty good about answering them. I've been working with Hadoop for probably around 3 years now. Kind of got started on a production Hadoop install, developing analytics and working with a lot of different Hadoop technologies, specifically like HDFS, MapReduce, Pig, Zookeeper, HBase Accumulo, things like that. Today, I'm going to be going over Hadoop, just the basics for big data rookies, which is going to include just kind of a brief Hadoop overview, what it is, kind of where it came from, pieces, why you all should care. There's a lot of you in this room, so I hope that you all have a good idea of why you should care. We're also going to talk about the HDFS architecture, kind of how that functions. The Hadoop MapReduce, the architecture of that system. I'm going to go into the Hadoop ecosystem, kind of a lot of the open source projects and other projects out there to kind of augment the Hadoop core of the file system in MapReduce. And finally, kind of a MapReduce primer to walk through, just kind of a Java code example of word count is typically the hello world of Hadoop, but also kind of discussing the individual MapReduce components that one would typically develop for that. So with that said, let's buckle up. I got about 70 slides of material in 90 minutes to do it. If you all have any questions, feel free to raise your hand, pipe up, write it down, shoot me an email. During this session, I won't answer it, but afterwards I'll answer it. So with that said, Hadoop overview. The Hadoop core project, it's an open source Apache project, mostly written in Java. It has some native libraries underneath it. Came out of Yahoo in about 2006, started by Doug Cutting. He's kind of the Hadoop overlord, I should say. At its core, it is a distributed fault-tolerant data storage and batch processing system. It's all about really, really huge data sets, storing big data. It was built to kind of deal with the whole new web age of how do I manage and store these massive files, and how do I process these massive files. It was built off of 2 papers from Google that came out in 2003 and 2004, or 2004, 2005, basically on the Google file system and Google MapReduce. How are they storing and indexing their gigantic data sets? And at the time they were developing this project called Nutch, they were looking at how do we store and process all this data, and they came across these papers, and they're like, sweet, let's develop them, open source them out to the community, and it blew up into this massive project that we have today. It provides linear scalability on commodity hardware. Commodity hardware does not mean cheap hardware, it just means cheaper hardware. You don't need any specialized systems to run these things, typically just Linux box, JVM, and you're pretty much good to go. Some disks and some RAM. And if you need more data storage and you need more processing power, you simply buy another rack, buy more servers, slap it on the system, and keep going. It's been adopted by many over the years. Amazon, AOL, Facebook uses it, Google even uses it, and many, many more people have been picking up this technology over time. So for why, the bottom line of why this system exists and why people are really getting into it and loving it is an extremely flexible system because it is a file system at its core. It's extremely scalable, and most importantly, it's very inexpensive. The software is cheap, free, if you go and download it from Apache, and the servers to actually run the software are also relatively cheap. So Hadoop is really great at reliable storage for multi-petabyte sized data sets. I believe the largest system now is around 45 petabytes of compressed data. Somewhere around, I think 4,000 nodes is the soft limit for Hadoop. So really, really big systems we're talking here. It's great at batch queries and analytics. These are your deep processing, your indexes, your hourly jobs that you're going to be running. It's not an interactive type system for executing this. You're processing petabytes of data, terabytes, gigabytes. It's going to take some time to get results back. So we're looking at really kind of batch processing here. Because it is a file system, it's really good for complex hierarchical data with very often changing schemas. You can write your applications to be aware of changing schemas and be schema aware. supporting unstructured, structured data inside the file system, whether it be images, videos, flat files that look like tables, whatever you can store in a file, you can store on Hadoop. The problem comes into actually processing that data, which we'll talk about later. It's not so great at changes to files in that you can't do it. Hadoop is an append-only file system, so you cannot go and flip some bytes inside this file in HDFS. You can only add data to it. It's also not very great at low latency responses, as I was talking about earlier. This is a batch system. Don't expect it to come back in milliseconds or seconds, rather. Also, analyst usability. And this piece really just means, a lot of DBAs, databases, analysts are used to speaking SQL. And until very recently, there was really no way to do that. You needed to develop custom applications, custom Java code, use higher level APIs to work with Hadoop. Overall specialists wasn't actually kind of available to, say, the enterprise. But now with tools like Pivotal Hawk and Cloudera Impala, Hive Stinger, which we'll get into a little later, that's kind of breaking down the barriers now and letting people that speak SQL and don't necessarily speak Java can actually use Hadoop. So what is actually stored on HDFS? It stores bytes. There's no ETL necessary or required for this system. Data lake is the term that's being thrown around now, that you take all of your data that you ever have and you throw it into this file system. You don't transform it on the way in, you don't touch it, you just throw it in there, and you define that structure of the data as you read it. So this is nice with the changing schema pieces. If you have new fields that come in, your applications can be aware that, hey, I'm going to see new fields, so let me read this structure from these bytes. Has built-in support for very common data types, like strings, ints, longs, byte arrays, as well as formats, whether that's just like a simple text file format, read one line per record, or say like Cassandra input formats for reading data from Cassandra, Avro formats, they have JSON formats, XML formats, so a lot of common data types to read any data that you put into Hadoop. And this structure is extendable, as we'll talk later when we get into kind of the component pieces of Hadoop. And also flexible, of course, for the structure pieces. Some versioning information. We're kind of in a transformation switch between kind of the first version of Hadoop and the second one. So version 0.20, 21, 22 kind of morphed into the Hadoop 1.0 line. And with that, from a programming perspective, there's two main MapReduce packages. Hadoop.mapred, which is deprecated, and then there's Hadoop.MapReduce. So some examples that you might come across with what kind of working in the blogosphere might be using this old deprecated package, but there's kind of less common now since everything's being updated to the new deal. Version 2, alpha'd in May 2012. This comes with the NameNode high availability HA that I'll talk about, as well as Yarn, which is kind of the next generation of MapReduce. The beta actually just came out a couple weeks ago, so very, very new technology, not even stable yet, I should say, but we're using it anyway. HDFS architecture piece. So when it looks like to users and clients accessing HDFS, it looks like a Unix-like file system for data storage. It supports common Linux commands, ls, make directories, cat, tail, like different pieces of a Unix-type system. However, underneath the hood, it's actually taking that data, splitting these large files into smaller chunks of data. 64 megabytes is the default. 128 and 256 are also very common sizes, depending on how big your files are. And it takes these blocks and distributes them among a number of servers, and then replicates these blocks. There's two key services. There's a master NameNode, a single service, that is basically a giant name server, kind of knowing where these blocks are inside the system. And there are many, many data nodes, up to 4,000 I was saying before, that actually restore the data. There's another service on the side called the checkpoint node. It used to be called the secondary name node, but that name has since been ditched because people were starting to think that it's some sort of hot backup. It's not. It just does checkpoints of the file system. The NameNode itself is the single master service. It was a single point of failure in the Hadoop 1.0 line. If your NameNode crashes, you can no longer access your data in the system until you bring it back up. With Hadoop HDFS 2.0, we have NameNode high availability that takes care of that single point of failure problem. it stores this file to block to DataNode locations inside the namespace, which is stored in memory. It's essentially just kind of like a triple map there. And all the transactions that work with are actually logged to disk in a simple log file. So whenever someone makes a file or reads a file or creates a directory or deletes a directory, all of these transactions are logged to disk. So if the NameNode were to fail, it starts up and there's kind of like a namespace image on there. It will pull that into memory, and then we'll start going through this log that it had and basically modifying its namespace over time until it comes back, it's read through all its transaction logs, and it's safe to actually use HDFS at that point. So the NameNode stores all these pieces in memory. In the event that it runs out of memory, it will then start spilling to disk, at which point it becomes very, very slow to use, which is not good. So typically, NameNode service in a production system has its own standalone server, and it's given all the memory on the box. Checkpoint node performs the checkpoints of the NameNode's namespace and logs. It is not a hot backup. If your NameNode fails, the checkpoint node will do nothing. You can schedule it periodically, say every day. It will load up kind of the most recent checkpoint, the namespace piece, much how the NameNode will load that up into memory. It will read through the log transactions and modify this namespace, and then save this namespace back to disk as the checkpoint. And this is useful so that your NameNode's transaction log that you've been running for months doesn't get massive. You can take daily checkpoints, you can back up these checkpoints as needed, put them on an NFS share, anything like that. These are all ways that they kind of tackled solving the single point of failure from way back when. The checkpoint node is still in the HDFS 2.0 line just to obviously take checkpoints over time, but no longer single point of failure. The DataNode service, it stores these blocks on the local disk that you've configured for that system. That's all it does. It responds to requests from clients for any input and output relations, for writing data and reading data. For a management side, it sends frequent heartbeats to the NameNode that just pings them and says, hey, I'm alive. That's about every 2 seconds. And it also sends block reports to the NameNode. It says, here are all the blocks that I'm processing. So the NameNode is keeping track of the system and what blocks each data node has. So in the event that a data node were to fail, it knows all these blocks resided on that data node, and I need to re-replicate all of this data. Yes?
How do you identify those data blocks?
So HDFS handles all of that behind the hood, or under the hood? Under the hood. So each actual file, you can look at a data node's data directory. It's blk underscore some number.
But the blocks of the file.
How do you identify them?
You have the file,
Mm-hmm.
which has an ID.
Right.
And you have the blocks of the file.
Yeah. So the NameNode is storing, so you put a file, just say my data in there. So my data, NameNode is storing that, and it chunked it up into blocks, which are some files. And those blocks are stored on data nodes. So when you want access to that file, you say, I want to read my file called my data. And the clients will make requests to the NameNode. It'll say, where is this file? And it'll come back and say, there are these blocks. I have a little diagram. We'll see this later. But yeah, I just remembered that. DataNode also does checksums on files. So if there's any bit rot on your disks, it'll make sure that those checksums for all those blocks are safe, and it'll delete blocks. It's a very fault-tolerant data storage system. So how it works when it comes to writes. I have a client here that's going to be a NameNode and 4 DataNode servers. So kind of the step one is the client's going to contact the NameNode and say, hey, I want to write some data. It's called this file. And the NameNode will respond and say, OK, write it out to these nodes. At which point the client is going to sequentially start writing blocks out here. So if I have a file called A, they're essentially split into 4 blocks, say a 256 megabyte file, split into 4 64 megabyte chunks, at which point the client then connects to DataNode and writes a block out. And then it will connect to the next data node as orchestrated by the NameNode. It said where to put all these blocks, and it will write out that next block. And finally, after the replication is done, which I have a slide on later for that, the data nodes kind of re-replicate all of this data in between themselves. So the client is only writing the file once, and it's essentially make 2 more copies inside HDFS. That's all distributed and replicated and blockified out there. And all this process is orchestrated by the NameNode. The data nodes don't really have any responsibility except for copying blocks to other data nodes and serving requests from clients. In the event of an actual node failure, say if DataNode D goes down, because these blocks are replicated in the file system, a client can reconnect to say A1 or A2 or A3 because that block is somewhere else on the system. And the NameNode will also recognize that, hey, this data node crashed, at which point it'll start re-replicating all the blocks on that node out to the other system. It's about 10 minutes, but that threshold's configurable, so you can restart data nodes if you want, but neither here nor there. So for the reading part of it, the client, again, is going to contact the NameNode and say, hey, I want to read some data. The NameNode responds and says, you can find all this data here. That file that you wanted to read out can be found on all of these data nodes, and these are all the blocks that it consists of. At which point, the client then can sequentially read blocks from these data nodes. It reaches out to, say, data node B to read the first block. And then once that block is fully read, it'll reach out to data node C to read that second block. And then once that one's read, it'll reach out to data node D and so on and so forth. And the way that these clients are built and implemented, they're all intended to be as data local as possible. So when it receives that block report back from the NameNode, it looks at all these blocks and say, okay, this block is on my local host, so I can just read it. It used to still go through the HTTP loopback, but they've recently put in a feature that it'll just read that block straight from the local file system. If the blocks are on the same rack, it'll reach out to a different node on that rack. If it's on a different rack, it'll reach out there. So by the way that HDFS kind of distributes data, a lot of clients can access this locally, yes?
Is it possible for a client to read data from multiple data nodes if the data is not distributed across those data nodes? Is that a possibility?
As far as the same block is concerned, like
Be replicated in other nodes?
so it won't read from both simultaneously. I think that's what you're asking. It'll connect to one and read as much data as it can, and if that were to fail, the clients will basically reconnect. So in this figure, say the first or the third block there, disconnected, it'll pick up from another data node, make another connection from that, since it has that block mapping.
Does the client get the full set of redundant locations of the
Yes.
file that it is asking when you download, or it is going to ask it again when it fails?
It uses all of that information, and it'll reconnect to the data node, and if that block isn't there for some reason, it understands that. The clients will make requests back to the NameNode if needed, but that report it keeps.
So does that mean that, like you are using this 3 replication,
Mhm.
which is like a good idea, but technically I could use 100 replication.
Right.
So in that case, the client would be like getting like 100 times the whatever, like let's say that 10 nodes are
Uh-huh.
recording my full file, so 100 times 10.
Yes.
Figure out there to get the data.
Mm-hmm. It's a lot of metadata coming back. Yeah. So how the block replication works, it's a default of 3 replicas. Any more than that, it'll just put them anywhere, as we'll see soon. 2 replicas is also pretty common just for smaller kind of development systems, because usually storage is pretty short on there. And if you have a 5-node system or a 3-node system, with 3 copies on a 3-node system, you're basically just copying your data to each node. So keep that in mind. It's a configurable parameter. Pretty much everything in this system is configurable. So you can configure Hadoop to be a rack-aware system, so it'll understand that these servers rely on this rack inside your data center. So if you have a client, as symbolized by this smiley face, you like my smiley face? Okay. On this side of this data node, when it goes out to write a block, it will write 1 block on the same rack. That first block of the file is actually written to that exact data node, but all the other blocks can essentially go anywhere else on the rack. So here it's writing it to a data node on that same system that it's running. If a client is not running on a data node service, it just writes it, just picks a rack essentially. At that which point then, this block, after it's finished writing, the data node will connect to the other data node service and copy that block over. And again, orchestrated by the name node, it says these blocks go here. And then after that's copied, this data node then will copy that block to another rack. So it's going to store 2 copies on one rack and 1 on a separate rack. And this is really useful in the event that someone trips over your wire in your data center and your rack goes down, because it has blocks on other racks that it can automatically recopy and distribute this data from. If you don't configure your Hadoop cluster to be a rack-aware system, it'll just put 3 copies wherever, at which point, if a rack goes down, then you're going to possibly have some data loss, and most likely you will. Features of HDFS 2.0 is the NameNode high availability. And with this, there are 2 redundant NameNode services that you can start up in either in an active passive configuration. So you have an active NameNode, and your data nodes are aware of both NameNodes. And they send block reports out to both data nodes. They use both the NameNodes as they are, except one is just considered active. So all like the various, let's say like write requests go through that. But for reading stuff, it'll use both NameNodes. So there's either manual or automated failover. You can do manual where if you want to take a server down for maintenance for the NameNode, you can, as an admin, say, switch over to that. And in an instant, that passive NameNode will become the new NameNode. And all the data nodes will know that, and it will go through that NameNode for all the connections, at which point you can do whatever maintenance you need and bring the other one back online. Or it's an automated failover through Zookeeper, which I have a little bit on later, where it'll basically detect if the NameNode fails, at which point it'll be an automated failover into that system. This is done through the Quorum Journal Manager. I left it out here. That's kind of the tool that is used to do this transaction pieces and redundancy between the 2 NameNodes. The other big feature that came out is NameNode Federation. So you can have multiple independent NameNodes that are using the same collection of data nodes. For in a multi-tenant system, if you have a huge cluster, but you kind of want to separate, this group has this Hadoop cluster and this one has that Hadoop cluster, you can stand up a NameNode per group, essentially, and set it up and secure it so that only this group can access this NameNode. And even though they're all sharing the same data nodes, the actual view that you see through that NameNode is totally separate. So that's HDFS in a nutshell. I'm going to go into the MapReduce components now. Hadoop MapReduce 1.x. Yes, sorry.
One question on multi-tenancy. Is that one tenant per NameNode as you federate?
Whatever you want. So HDFS has like Linux type users and groups, and you can secure it using Kerberos or other LDAP authentication. So you can stand up a NameNode and basically say, these users that are consisted of this group, they can go through LDAP and talk to this specific NameNode or another one. So it's not one per user. You can set it up that way if you want, but however you want to. So Hadoop MapReduce, I'm going to be talking about the kind of first version of this and the architecture pieces. The whole design behind this is, I'm storing my data. It's distributed, replicated across my cluster. Now, how do I go about processing that in a nice parallel way? And from traditional applications, you would move your data to your processing application and do it there. MapReduce is a whole new paradigm in which we are going to take our code, our application, in a JAR file, and we're going to ship it out to all these nodes, which are going to process the data locally on that system that's out there. There are 2 main services, or only 2 services. The job tracker, which is a master service which monitors and schedules all the jobs that are submitted by clients for the system. And the other piece is a task tracker, which is another multiple service that runs tasks. And these task trackers are running on the same physical machines that the data node processes are running in order to get that data locality. A MapReduce job contains many tasks. The number of tasks is equivalent to the number of blocks when dealing with HDFS input, the default. So that file we had earlier, that was 256 split into 4 pieces, you would get 4 map tasks to read all of that data in parallel. And each task has 1 or more task attempts to actually process that data. So if a task were to fail, whether that be an array index out of bounds exception, which I get often, or a null pointer exception, or something weird happens on the machine and a task were to fail, the job tracker will receive notification of that error and will start that task over again as another task attempt. By default, if 4 task attempts fail that belong to the same task, your job fails as a whole. So you can have thousands of failed task attempts as long as it's not 4 from the same actual task number. So the job tracker monitors your overall job and task progress. It keeps metrics about the jobs, bytes in, bytes out, number of records processed, number of groups processed. Any custom counters you developed in your application are all stored on the job tracker. When it receives job requests from clients, it takes that code, looks at the input files that you've specified there. I want to process, myfile.txt. At that point, it works with the NameNode, and just like any other client, says, hey, where are all these data blocks at? And the MapReduce code will look at that. It'll get that block report, essentially, from where these blocks are in the cluster, and it will start issuing task attempts to task trackers that are running on that same node where that block is. So 4 retrying failed attempts, 4 failed attempts is 1 failed job. The default scheduler is a FIFO scheduler that ships with it, which is funny because they tell you not to use that one and use the affair scheduler or a capacity scheduler. The problem with the FIFO order is that if a very huge job is submitted that runs a lot of data, if you have other jobs that are coming in that aren't processing as much data and might finish very quickly, that huge job is basically going to block all other processing until it's finished. So the fair scheduler kind of balances the distribution of tasks across multiple jobs. So overall, everything, I guess, takes longer, but those quick jobs will finish much faster rather than blocking by the FIFO scheduler. Yes?
Does the capacity scheduler take into account varied server capacity? So you can have 3 boxes that are powerful and another 2 that are not so powerful?
Not now, not this one. In the YARN framework, they're working on kind of developing that to know more about the resource allocation. The kind of piece that ties into a little bit of that, which you can play around with, is in the task tracker side, there's a configurable number of map and reduce slots. So each task tracker, you can say you can run 4 map tasks and you can run 4 reduce tasks, or any combination of that. The usual rule of thumb is 1 task per physical core on the machine. So if you have more powerful machines that have, say, 4 sockets rather than 2, you can configure that specific task tracker to run more processing power on it. But it doesn't do that auto-magically, unfortunately. Task trackers, they also send heartbeats and task reports to the job tracker. And it runs map and reduce task attempts there. It runs all these in a separate JVM. From the actual task tracker, so if something catastrophic happens, it won't take down the task tracker along with it, just that specific JVM. Yes?
So it's 1 JVM per task, so
So the DataNode is a JVM, the task tracker is a JVM, and all the tasks that are running are separate JVMs as well.
each task is 1 JVM?
Yes, yeah. There is configuration to essentially recycle JVMs. The default is 1 per task. So if a task tracker receives another map task, say, for the same job, it'll recycle it using that same JVM. So talk a little bit about exploiting data locality in here. This job tracker will schedule a task on a task tracker that is local to the block. So with a 3-time data replication, the job tracker basically has 3 choices to choose from at that point. If those task trackers, those 3 that can process that data, are too busy, it'll pick another task tracker on the same rack of those 3. So you have 2 blocks on one rack and 1 on another rack. So you basically have 2 racks of task trackers to choose from, which there are lots of options there to run it. And if for some reason all of those task trackers are too busy, it'll just pick another free task tracker at random and run it there, which is rare, but it happens, especially for very busy clusters that are running at capacity all the time. And with the metrics that print out at the end of your job, it'll say, this is how many data local tasks I had, this is how many rack local tasks I had, things like that. So how it works overall, you'll have a client that'll submit a job to the job tracker, and inside of that it contains my input path, which can be files, folders, wildcarded paths, as well as your kind of like input formats, my output key value pairs, which I'll talk about soon, any custom code that you've written. Basically, your application then gets submitted to the job tracker. At which point, it'll figure out where those blocks are, and it'll start submitting tasks over to task trackers. Here's this file A that we're processing. This is one node of DataNode A and task tracker A that are running. And all these tasks are going to be run, and all the output then is going to be spit out to HDFS with, again, that'll be replicated and running again. So kind of each of these task trackers, when it's writing output to HDFS, acts as a client, essentially. So when it writes it out, it'll get that local block, one on the same rack, one on another rack as is. And once the job completes successfully, it'll report back metrics. You don't actually get your output like you may be used to using a SQL type prompt. It'll just say, my job is finished, at which point you can go fetch your data, you can export it to another system, you can do whatever it is you want with it after you've processed it. In the event that a node were to fail, job tracker will receive notification of that, and we'll just assign it to another task tracker. So much how the HDFS is very fault tolerant in replication of the data, the replication is also seen here in replicating actual processing tasks.
Does the client has to wait for the execution finish, or just submit and I come back later?
Both. You can choose. So there's, when you submit your job, the question was, does the client just submit and lock or wait, or can you just submit and keep processing? There's two ways to do that. You can either just submit the job and the application will continue running. You can do whatever. You'll get a job object that you can check status of periodically, pull counters out of, things like that. Or you can just say wait for completion. It's job.wait for completion, and it'll halt in that application until it comes back. So Yarn, which is yet another resource negotiator, they kind of took, looking at MapReduce and what it is at its core, they wanted to add another abstraction on top of that to make just a general framework for distributed big data or other type of applications. So they're looking at the job tracker, there's two main pieces of it. One is the resource manager piece of how am I going to schedule and distribute my application into my cluster. And the other piece is the actual application master, which is the application monitoring piece. So they split them up into two pieces. So and they converted the task tracker piece into a node manager. So one of the complaints with the task tracker is you have, since there's a configurable number of map and reduce slots, you could have all of your map slots filled and none of your reduce slots filled, and that's wasted compute power that's happening. They're just sitting there. So with the node manager, they use a notion of a container. And a container is a piece of compute power, essentially. Right now, it's just how much memory do you need? So each node manager has a configurable amount of memory that you want to give for processing power. And with that, each container has a default limit. So say 8 gigs for processing, and I want 1 gig containers. So this node manager can run 8 processes, essentially. So when a client requests a piece of compute power, a container, it sends along with it, this is how much memory I'm going to need. And Yarn will monitor that and make sure that you're actually using that much memory. As they develop the Yarn framework, they're going to put pieces in like how much CPU power do I need, how much disk do you need. They're going to use like a full resource manager framework for distributed applications. So MapReduce 2.0 on Yarn. The MapReduce API hasn't changed. All you need to do is develop your MapReduce job that you've developed against the 1.0 line. You just change your dependencies and rebuild. And that's good. I actually think I read in the beta release of 2.0 you don't need to do that anymore, but I haven't tested it. You can just run your old code on Yarn. So the application master piece is per application. So MapReduce has a MapReduce application master. HBase is also in the Yarn framework now, and it has an HBase application master. And the MapReduce essentially is responsible for launching this job. It needs to figure out, where am I going to put tasks? I need to request containers from the resource manager of Yarn to distribute out my tasks. And there's also another process called a MapReduce history server, which is just a web server that is used to store the history pieces of it. So all this kind of job tracking history pieces isn't in the Yarn framework. It has that for applications, and a job is a type of application inside of that. So whenever you submit a job in MapReduce, you're basically spinning up an application master per job. So before I go into the actual, like, what does MapReduce look like from a developer standpoint, I kind of wanted to go over the actual ecosystem. So there's two core technologies that came out of this. When people are talking about Hadoop core, they're talking about the distributed file system and MapReduce. And there are many, many other tools that have been cropping up over the years to kind of counteract different pieces or limitations of HDFS and MapReduce, which I'll be going into now. So we're talking about moving data. I have my Hadoop cluster. How do I migrate stuff off of my old SQL systems? How do I get data into it in a nice, clean way? There's a project called Scoop, which is for moving data between a number of relational database systems and HDFS, both in and out. So you can schedule Scoop jobs and say, I want to move this table into Hadoop, and it'll go off and do everything it needs to do to take that data and put it into HDFS. So if you want to migrate some MySQL tables into there, that's the project to use. And Flume is another project, which is all about kind of streaming event data from sources to sinks. Very abstract. You know, what is my source, whether that be a web server or an FS share or a Twitter stream, whatever that is, and what's my sink? Where am I going to put that data? Is it a database? Is it HDFS? Is it my local file system? Whatever you want.
When you are moving the database table to HDFS, what's going on?
You can either do, I guess, like the Oracle files, or it can just be flat files. Like you can, I guess, pick which format you want it to be.
But basically, I need to process the flat file later on as a text, reading as a text or something.
Right. Yeah. So if you, like pulling a table out, it'll just, you can store it as a flat file and then process it line by line using MapReduce. The Flume architecture, there's three main components: a source, which we're talking about, a channel for how am I going to move data from my source to my sink, and an actual sink in this piece. So there's a number of sources that have developed and shipped with Flume. You can develop your own if you feel like it's pretty easy. So the original thing was like moving log files from web servers. So you can write Flume agents that will sit on your web servers that will basically look at log files, and it can tail them, and it will push them through a channel. And the channel can either be like a local file system, so kind of more reliable system, it'll write them out there. Or you can just use an in-memory channel, that's pretty common. And then a sink of where am I going to put that? HDFS is a good example. I wrote recently a Flume agent that would pull from the Twitter Streaming API and write to Greenplum database using a JDBC connection. It was god-awful slow, but it did it. So I'm working on that. So kind of higher level APIs, there's two main ones. Pig, which came out of Yahoo a little while back, and Hive, which was originally developed by Facebook, and now Hortonworks kind of spearheading the development of that project. Both open source Apache projects. Pig is described as a data flow language, which they have called Pig Latin. The shell that you interact with Pig is called Grunt. The Eclipse plugin is called Pigpen. There's a lot of various Pig-related items. It's great. So Pig, you express, using this data flow language, it will take that script, that Pig script, and will generate one or more MapReduce jobs that are just Java MapReduce inside their Pig framework that will execute on your files in HDFS. So it's really great for prototyping, or if you have like hundreds of things to do per se, like you don't want to spend all day writing MapReduce code to just like group by, sort, and join on this. So Pig has all that framework in there to use a lot of the SQL syntax we're used to. Hive is a data warehousing solution. So you can write SQL-like queries that will also generate a series of MapReduce jobs. Both of these projects started around the same time when they realized, hey, I'm copy-pasting a lot of my MapReduce code to do the same stuff over again. So why not write a higher level language with that? So for the word count example for Pig, just to kind of give you a little glimpse of it, over here on the left are they're called relations. So it's basically a variable that you're looking at. I want to load my input. So $ are variables in Pig that you can use and specify in the command line. So I'm going to load input, and I didn't specify a schema here, so it's just going to load one line per record. And next here, for each line in A, I'm going to generate something. So $0 is that first index. That's the line. You can use positional notation. I'm going to tokenize it. And tokenize is a function that comes with Pig that will basically take your input and will split on white space, commas, and like underscores, and a few other things. And flatten is a special operator that will basically take that tokenized string of all of my words in my line and will kind of pivot it on its side into another piece. And we called this thing word. So B is essentially a massive list of words inside my document that I've created. Next, I'm going to group this giant list of words by word. So this creates a MapReduce job where the key, which we'll see later, is the word, and the value is essentially the word. So it's building these groups. It's essentially, the, and then a giant list of thes, and atom and a giant list of atoms, things like that. And the last line here, for each one of these, we're going to generate 2 columns, one of which, so this group by operator creates a thing called group, which is what you grouped by. In this sense, it's word. And I'm going to run through this UDF of count, B. So this will basically iterate through that list of words and count how many things were inside of that bag. And then I'm going to store D into an output directory. So there's a store command which will, at that point, execute your MapReduce job, submit it to the YARN framework or job tracker, depending on what you're using. It will run all that processing and will dump stuff out to HDFS. There's also a dump command which will just write it to standard out for kind of development here. So with Pig's supporting operators like distinct and joins, both left, outer, Cartesian products, like there's a lot of tools here for actually writing MapReduce jobs. So using a higher level language like this will get you, say, 80% there for all of the MapReduce processing you need.
I think that by obviously having all these steps, creating independent MapReduce, so you have a bunch of extra, are you having extra storage necessity for this, like extra files being processed? And at every step is output, and then you somehow measure that this is my actual expectation on it. Let's say I'm processing a petabyte of data.
Right.
How many more petabytes I need to get to the result?
Yeah. So the question is, it's create multiple outputs in the series of it. So for each step in the process, Pig has an optimizer, so it will do what it can to reduce the number of MapReduce jobs overall. But for each MapReduce job, it's writing the output right back to HDFS. And this is, for Pig, it's in like the temp directory of Hadoop. So it's writing out that data, and then that data is going to be used as input into the next job. And this is the same way that you kind of chain jobs together using MapReduce itself.
Yeah, but what I'm asking is that is there some measure or some type of way to kind of guess what is that size already?
As far as like output?
Yeah.
Not really, I guess. You would need to kind of know your data and the processing that you're doing. When it comes to tuning jobs, I would typically just run it and see like how much is input, how many tasks are created, how much output is it creating, and then you can play with the parameters to make the best of it. Pig will, as part of its optimization framework, it'll actually guess what the output is and use some of that in its optimizer piece of it. But that's magic underneath the hood. Yes?
You can run the Pig script on the master NameNode, or where do you run it from?
So Pig, you can just run it from whatever client that has access to your job tracker.
To the master NameNode, is that how it works?
It will, yeah, so like Pig is just a jar file. You don't have to actually install anything. You just unpack it and put it on your path. And when you start writing stuff, the JVM that's running Pig, your client essentially, is kind of compiling your MapReduce code, and it will build a jar file and submit it. So it's basically the same process that you would do if you just build a MapReduce, just Java client as a developer, except you're expressing it through this higher level language. And you can, clients only, they need access to the job tracker essentially. So typically, as far as like cluster layout is concerned, you would have a few nodes in your cluster for actual job submissions, rather than kind of submitting it out of the cluster. but that's up to you all. So for key value stores, there's 2 out now, HBase and Accumulo. HBase was the first one that came around. They're both implementations of Google's Bigtable paper that came out. It provides random real-time access to your big data and supports updates and deletes of this. So this solves the problem of how do I change my data inside HDFS. So the actual architecture of this, it's a little bit cut off there. So Zookeeper is there. I'll talk a little bit about what Zookeeper is. But there's an HBase master service that's running. And it's kind of like a NameNode in that it is a single master service that knows about these region servers that are inside the cluster. So these region servers are responsible for hosting regions. And regions are much like a block is to a file in HDFS. And then you have a store, which is basically a chunk of the region, let's say. And as of the store, there's a mem store, which is all the in-memory pieces of that. And then there are these things called store files. So whenever that memory gets full, essentially, it will write a store file out to HDFS. So there's this in-memory layer sitting on top of HDFS that responds to client requests. So when you want to, say, like fetch a record out of it, the clients, a lot of the metadata is stored in Zookeeper, so clients don't actually ever have to communicate with the master. So the client can figure out from Zookeeper, get the metadata for a fetch operation. And the clients will then connect to the region server that's hosting that piece of data. These are, logically, it looks like a giant sorted list by key. So by kind of knowing that this key and this key is the start of this region, the clients know that, hey, I want to fetch this key. It fits here in this sorted list, so I need to go talk to this region server to fetch that data. So the region server at that point will check its mem store and say, hey, do I already have this key there? If it's not, then it'll open up that file in HDFS and pull the data out of it. So there's a lot of data moving in and out between the region servers, but it supports there for kind of updates and deletes. So when you put a delete record in there, it's not actually deleting anything. Inside that mem store, it knows, hey, I deleted this key value pair. So when a client goes to fetch that record, it checks its mem store and says, hey, I deleted that key value pair. And there's a number of compaction schemes that run for these store files. So for a lot of these like updates and deletes, they're written out as store files, and when it runs a compaction, it basically drops all the data, kind of like a vacuum piece. That's HBase in a nutshell. And the Accumulo architecture is very similar to this because they're both based off of Bigtable, which looks a lot like this. There's a whole lot more into HBase that I don't want to get into. Yes, there's a question?
Just high-level HBase, I'm just trying to picture the use case.
Uh-huh.
When this will be used. Is it essentially an interface into HDFS that any client would go through, or
So,
does it have a specific place in the ecosystem?
uh-huh. So the question is basically use cases for HBase. Where does this fit in? So HBase and Accumulo are optimized for very fast fetches of pieces of data. It gives you relatively real-time access to it. So where MapReduce is a batch processing system, if you have an application where you essentially have like a massive, massive table, billions of rows, millions of columns, but you just need to fetch this one piece of data out of it. In order to do that in MapReduce, you have to read every single byte inside of it. But if you just want to get that record really quickly, this is where HBase fits in it. Because it's a giant sorted list of key value pairs, it knows this key I'm looking for exists on this region, so I can go directly to that region to fetch that data. And it has a number of optimization pieces of it in like block caching. So when you fetch a key, it will actually pull a number of keys into memory. So if you're looking for keys that are near that key sort-wise, it already has that stuff in memory. Facebook actually uses it to back their entire messaging system, which I think is pretty cool. They have a really cool architecture. You can look it up. For data structure pieces, Avro is a data serialization system that's specifically designed for Hadoop. They're kind of trying to solve what is the common data format for this system? Yes?
Just a quick question on the previous slide. So basically using from the region server using indexing, what is the cost of that? And how much more memory?
So the indexing, it's an H file as it's stored. So that actual block, it keeps not that much, I guess. Like it's not storing that whole block, but for 64 megs, it's a few K that it'll keep. It says, this key is at this byte offset in this file. It also has Bloom filters, if you're familiar with those, to put on top of these. So, it'll check its Bloom filter, which is in memory, before it bothers going to the file for any false negatives, things like that. So Avro is expressed as JSON. It can run as a server or as a file format to kind of flow data in between pieces. But this is really just trying to solve, common data format for Pig, Hive, pretty much across the whole ecosystem. Avro is also designed for Hadoop in that it supports a number of types of compressions at the block level or the record level. It has headers at each of the files. So problem with some hierarchical data sets is it might be split across boundaries or other things. So Avro's smart enough to not do that, I should say. So if a JSON record were to overflow into the next data block in HDFS, Avro is smart enough to write it to another block, and it'll have a header on top of that of, this is what my data looks like. So when MapReduce runs over, it'll read that header, and it'll just process all the data. Whereas having a header at the very top of the file, every single task tracker would need to read the top of the file, which is on some other system. So a lot of optimizations in there for HDFS. Another one is Parquet, which I don't know much about. It's a columnar format. I believe they're looking at since HBase is a columnar data store, they're kind of looking at using Parquet as their storage format. Can look it up. I haven't played with it yet. For scalable machine learning, is a library called Mahout. For scalable machine learning algorithms in Java, for classification, clustering, pattern mining, collaborative filtering, a lot of other pieces in there that are implemented in this library. It has a very robust example framework, which is why a lot of people will just use it, but there's like tons of parameters to configure for each piece. Another other thing is it's really intended as a library for you to develop these machine learning applications. It just has a lot of cool examples. For workflow management, there's a project called Uzi, which is designed for Hadoop jobs running Java MapReduce, streaming MapReduce, which I'll talk in a little bit, Pig, Hive, Scoop. DistCP is a special type of MapReduce job to basically copy one file from either a Hadoop cluster to another Hadoop cluster or just copy it all in parallel. And it'll also run any Java or shell script program. And it's all workflow system. It supports job dependencies, and it'll order everything for you. Cool little tool. For real-time stream processing, there's a project called Storm, which is not a part of the Apache Software Foundation. It was started by Twitter. It is all about streams of data called a spout, which is signified by the spout in this diagram. And it executes, there's also running a series of execution engines, which they call bolts, which are just pieces of processing, whatever that may be as you've defined it. It is very scalable and fault tolerant with basically guaranteed processing of data. So each one of these spouts creates an event, whether that be a tweet or a piece from your log file, and you can define your topology that from this spout, I want to go to this bolt, which goes to this bolt, or I want to fork off to these other bolts. So you can string together a series of operations that say, update your Redis instance with latest hashtag counts. Like they're using this to drive on Twitter, what's currently trending. This is from their live stream, they get pretty much instantaneous feedback from that, from their streaming data. It's been benchmarked of over 1 million tuples processed per second per node. So extremely, extremely fast real-time processing system. For distributed application coordination, you have Zookeeper, which the tagline is, it is an effort to develop and maintain an open source server which enables highly reliable distributed coordination. It handles all the things that you need to deal with in kind of like distributed application development, such as, how do I do group, leader elections, group services? How do I manage configuration for all these applications? You can go through Zookeeper. It looks kind of like a hierarchical file system. where there's a bunch of Z nodes. Here we have like 2 apps and another pieces, and each Z node acts like a folder and a file holding about a megabyte of data is the hard arbitrary limit that they have. It's really intended for metadata, and applications can kind of watch these nodes. So say I'm watching app1 p_1. If any other client changes that data on that node, I'll receive a notification of it. So this is really good for configuration, that if these were all configuration parameters, and I, as just an administrator, want to update the configuration for all of my distributed applications, rather than modifying an XML file and pushing it out and having to refresh or do a lot of management, I can go to Zookeeper and just say, change, all my applications will receive that new parameter, and you're all good to go. HBase and Accumulo both use this for their configuration management, as well as kind of knowing where regions are inside the system. So if you have HBase, you have Zookeeper. Kind of the quick architecture piece of it. Usually 5 Zookeeper servers is enough for hundreds of nodes to manage. There's a leader server that's elected upon startup, and a number of clients. You can connect to any server. It does synchronous writes to all the other Zookeepers. So these are all sharing the same namespace. So clients can read data from any server. However, all the writes need to go to the leader. So whenever I want to change anything, I go to the leader, at which point the leader will propagate that change down to the other Zookeeper servers. The Hadoop Streaming Library. It's a really quick way to write mappers and reducers and other pieces using standard in and standard out. So any type of tool that supports standard in and standard out, you can essentially write a mapper code for. And then you execute on the command line. This is very similar to how you do it just for any normal job. You do Hadoop jar, you give it a jar file. Here's the Hadoop Streaming Library. So you can specify input, output, the mapper class you want. This is the default mapper, which we'll see shortly. And reduce, I'm just using /bin/wc. So the Hadoop Streaming Library will go out. It'll use this mapper, that input, that output, and we'll run this WC program over all of them. I don't know if that's how you actually execute it, so don't copy paste it because it might not work. But that's essentially the concept of it. So like you can write Python scripts and Perl scripts and a number of other pieces to execute MapReduce code. It's not the best for production pieces. Like it's a little wonky of using it, but if you want to like prototype something, it's painful to like, I got to open up my Java and get Eclipse set up and like make a new project. It's like I just want to do some like simple Python script and get it out there and see what's happening. Really useful for that. The next piece is SQL on Hadoop. There are 4 that have kind of sprung up in the past couple years, one of which is Apache Drill, which is being spearheaded by MapR, Cloudera Impala, being written by Cloudera. Hive Stinger is an effort by Hortonworks to basically make the Hive project 100 times faster, as they say. And there's Pivotal HAWQ, which is our offering. And it's all massive parallel processing of SQL queries against HDFS data. Their architectures are relatively similar, but it doesn't run any MapReduce at this point. So the HAWQ architecture, you have a master server and a standby master there. So the master server responds to any SQL queries, inserts, updates, anything like that. It handles all the parsing, query optimizing, pieces like that. And it will dispatch SQL queries out to these segment servers and segment servers. And the segment servers are running on the same host as the data node, just like a task tracker or a node manager is running there, to process all this data. And the data is being stored in HDFS. HAWQ supports external tables, so you can just point it at files in HDFS and it will read that data. It is much more performant if you store it in HAWQ's native format, because if you're familiar with the Greenplum database, HAWQ is it's basically the Greenplum database, but it stores data in HDFS with a few other caveats there. So the query optimizer is very advanced in that, when it goes by distributing data, it can pick optimal query plans, but when you're just reading files, it has no idea how that data is actually physically stored, so it basically needs to read everything. That's the minute of HAWQ. Yes?
So this is very
So HAWQ there's the Greenplum database, which is, as is, that's not going anywhere. HAWQ is architecturally similar and shares a lot of the same code with it. HAWQ can only run on Pivotal HD for a number of reasons, some of which are technical. They're working on pushing back a feature that they had to add to HDFS in order for HAWQ to work to get its ACID-compliant transactions. Since Hadoop is HDFS is a depend-only system, if a transaction fails, you need to roll back that transaction, and you can't do that in Apache HDFS. So they added that feature there for it to work. So that's a lot of projects that you need to manage. I'm missing several. Sorry if I didn't mention the people who are running Apache Hadoop projects. I have my own. I didn't mention it. It's fine. So each one of these kind of cropped up to solve a general limitation of Hadoop. How do I get data into this file system, Flume and Scoop? How do we take away all this boilerplate Java code, Pig and Hive? How do I update my data in Hadoop? How do I, can we have a common data format between all these pieces? They've been developed over time. Each one has a very specific piece. It's good to know your ecosystem. That's kind of why I wanted to walk through this with you. And you need to kind of pick the right tool for the job. So I kind of whipped up a little sample architecture just to give you an idea of how this kind of all fits together. So say I have 3 data sources, my web server, like sales on my website, and like a call center that's coming through. So 3 very different types of data sources. And at the end there, I want to have my website that has my user sitting there who wants to get some meaningful stuff out of it. I got a couple left. That's all I need. So what you're first going to do is stand up Hadoop. You install HDFS. Maybe I'm going to have a couple Flume agents that are running here that are going to take my data from my web servers and all my other systems and put them into HDFS. Say I want to get some kind of like real-time metrics coming out of my sales data. As they're coming in, I want to update my website of what people are really interested in right now. What are they looking at to target my consumers better? So I'm going to put Storm in there, because that's my real-time processing piece. And I'm going to have these Flume agents. I'm going to write a Flume agent directly into Storm. I'm going to have a Flume sync that is essentially a Storm spout. That sync is going to write to this Twitter Storm spout. I'm just going to also pipe this other data into HDFS. And let's say I want to have Storm, it's going to write out. So I got a bolt to update my website with the latest metrics. I got a bolt that's going to stuff this stuff into HBase for easier access later. Potentially by my call center. I built an application that can query data in HBase. So this is that kind of fast fetching piece that I'm talking about, where a customer calls me, they have a problem with an order, I need to pull up that order data. If it's just flat file sales data, I can't get that without running a MapReduce job, and that can take potentially minutes. That's not good. So my application uses HBase to basically fetch that order number and bring it back to me in order to help out my customers faster. And HBase, of course, is storing it in HDFS. And then, I want to get some intelligence out of this. So I come up with some MapReduce jobs, some Pig to look at the data that's in HBase. It can read HBase data. It can read HDFS data. Whatever analytics you kind of want to come up with here. And of course, I don't want to run all these by hand, so I'm going to use Oozie to schedule my workflows and manage it. And it will restart any failed things, a lot of good pieces for that management there. And then with SQL and Hadoop, my people in the call center, they might know SQL, they may not know Java, so they need to kind of talk SQL. So I have this SQL on Hadoop offering that I can, read data directly from HDFS, Express, do deep analytics, do other interesting things with it. And I have some recent college graduate DBAs that, they didn't learn Java, which is very rare these days. They're teaching Java in school. That's another thing. They can also use the SQL interface into HDFS. So, you kind of got to think about, where am I heading? What is my solution? And how do I plug in these different pieces of the Hadoop architecture to fit in there? It's a lot of things, obviously, to manage, and each one has its own caveats, and some are really good at things and some aren't, and that's up to you all as the developers in the Hadoop ecosystem to figure out. Sorry. Yes?
When you're saying use SQL some query on HDFS,
Mhm.
you actually assume that I'm running on those HDFS files which are created by
Mhm.
or one of the other
Right.
SQL kind of simulator or
Mhm.
something. But basically, I'm talking about different sets of data.
Right. Yeah.
All these are kind of not really the same data yet. So
Mhm.
they're
Yeah.
just using the same one.
Right. So the question is mainly about data formats in here. So, for Pivotal Hawk, it likes to store data in its own format, but using PXF, the Pivotal Extension Framework, it can virtually read anything that you can split, like MapReduce. So it can read line formatted data, it can read Avro, it can read sequence files, which is a special Hadoop data type. It can read, I built an extension for JSON, I built an extension for Cassandra tables. So through the extension framework, you can put basically a SQL interface on pretty much any data type that can be processed in parallel. And some of that is more difficult than others. So you can do inserts into Hawk and it will store the data as is. That could be another piece of, using Flume or batch processing and dumping stuff into the SQL and Hadoop offerings. Like Impala and other things, they can read Avro and another of other formats. So a lot of this, if you want to start joining your web server data with your call center stuff, so with the MapReduce input formats that I'll talk about next, it's kind of, how do I read my data? Since I'm storing it unstructured as is, I need to now read that data. And that's defined in your code and how you're reading it. Both, how do I read it? Is it a block of bytes to form an XML record? Is it one line? Is it an image that I'm reading in? And also how to turn that into something tangible for processing, which we'll see soon. Yeah.
Is there a metric or something where a regular database just won't do? Where's the tipping point?
Uh-huh.
Go into this instead of just
Uh-huh.
put a job on top of a SQL server.
So I recommend, the tipping point is really I have too much data to handle. I can't do it in either. So some problems with that is they don't know that you don't have much data. You can get a lot more. With Facebook turned on their clickstream logging and they got way more data. They had a 10 terabyte Oracle system for millions of dollars. And they turned on the clickstream stuff and they were getting more data than they could load into their system. So they went to this project because they were getting way more data than they could handle, way more data than they can process. 10 node systems are pretty common, but if you're kind of less than 5, it's not that much storage, that probably a database would be a better fit. This type of technology is really for those that have a big data problem and that don't want to spend a lot on kind of scaling up your technology. So if you expect to grow your system, grow your data size, rather than adding and scaling up vertically on your hardware, you can buy more servers and add them to your Hadoop cluster over time. And it's cheaper. People like that.
So many terabytes a second.
Right.
How many terabytes are we talking?
More than, I don't have a good number for you. Tens, dozens, terabytes. When you're talking petabytes, this is definitely where you need to head towards. Yeah. Mm-hmm. So MapReduce paradigm. This is just MapReduce, and then I'm going to talk about kind of the Hadoop pieces of it. MapReduce is a data processing system with 2 key phases that are called map and reduce. You all could have never guessed that. So the map performs this map function over input key value pairs to generate intermediate key value pairs. So that piece of code, that piece of processing is up to you, whatever that is. Whether I'm doing a word count, whether I'm pulling stuff out of an image, whether I'm ripping images out of a PDF, whatever it is. It has input key value pairs and output key value pairs. And then there's a reduce phase, which performs a reduce function over intermediate key value groups to generate output key value pairs. So the stuff that is output from the mapper is input into the reducer as groups. And these groups are created by sorting the map output on key. So before with the pig example where I was saying, group by word, the key is a word, and then essentially the value is a 1. So when this sorting happens, when this grouping happens, on the reduce side, it's going to get a key, which is a word, a unique word across all the systems since it was grouped by it, and a list of values that were associated with that. And we'll see that soon. So this paradigm fit really well for Google because it's extremely parallelizable algorithm. So since you're operating on key value pairs, it doesn't matter where these key value pairs came from. So I can really distribute this application to read data blocks, create key value pairs out of them, and do some processing on them, and then spit out this. They were using this to essentially index the internet, which is sweet. So for my example here, I'm just going to walk through word count. So for map input, say I have 3 map tasks, and each one is going to process a single line of data. In Hadoop, the key for this one is the byte offset of that line, which is typically useless. And then the value is going to be that line of text itself. So this is the key value pair I'm going to get for each call to my map function. So that block has several lines in it. So this mapper is going to get 1 map call per line, because that is how I've defined how I'm going to read my data. How do I create key value pairs out of this? So the map output of this in there, I'm going to take that line, chunk it up into words, and then output the word with the count of 1. I saw this word 1 time. And all of these tasks are happening in parallel over the system. So there's this middle phase here called shuffle and sort, which I'll talk about soon, that kind of goes over how do I actually make these groups together. So it's a group by key. So here we have fun, Hadoop, love, and I, and a list essentially of ones. So this is the group that's created. This fun from here and this fun from here are going to go to this reduced task. There's no fun over here. So at that point then, this reduced task gets this group, and it's going to go through that list and sum up all the numbers. So I have an output word of fun and then number of 2. And all this output is then going to be written back to HDFS. So this is it, basically. It's all key value pairs. Whatever you can fit into this framework is good. It's obviously very, very simplified in this, and like Pig is running this behind the scenes, so they have their implementation of how they do distincts. So this is the boilerplate of group by is I'm going to take whatever I'm grouping by, set it as the key, and then that record's going to be the value. So the different MapReduce components. In the map phase, these are all Java classes that you can implement. There's an input format, a record reader, a mapper, a combiner, and a partitioner. So the input format is how do I split and specify my data? What format is it? Is it a text file? Is it an Avro file? Is it a sequence file? Am I reading from a Cassandra table? The record reader is how do I take these bytes that I'm reading from my split and turning them into key value pairs? Is it a line? Is it word by word? Am I pulling in a chunk of data? Am I reading an image from these bytes? So this is where that kind of changing schema stuff really comes into play here. If I can get some metadata about my schema in the Avro sense, that block is, the header is there on that block, so you can, read it. The mapper is your code, how am I doing my processing? The combiner is a special component that I won't really go into. It's kind of like a mini reduce over that specific map output. The partitioner is how am I going to distribute my data to these reduced tasks. And then in the reduce phase, there's the shuffling, which is the actual copying of the key value pairs to those reducers that were partitioned, the sorting of the data, running the reducer for the groups, and then of course you have a corresponding output format and a record writer. How am I going to write out these key value pairs? Is it 1 per line? Am I writing an Avro file? Things like that. And the record writer is how are these bytes physically written out, or how are these key value pairs written? So there's writable interfaces that are basically serialization for the data. There's a writable that takes in a data output and a read fields, which takes in data input. And there's a writable comparable, which extends writable and comparable. So these are kind of the key value pair data types that exist. There's numbers out of the box, Boolean, bytes, long, int, a lot of pieces for that. Writables, you can write your own custom writables if you have your own special format. You can do that. Input format is an abstract class templated to those writable types for the key and value pair. There's one function for get splits, which will take that input that you have and figure out what are the actual input splits in my job, and it returns a list. So these are that blocks locations that we were discussing earlier. And there's also a function to create a record reader that is templated to those same data types. The record reader has an initialize function to start this. Typically for a data block, you'd open up the file, you would seek to the start of that data block, which is going to be on that same node, and that's pretty much the initialize piece. So there's a next key value, kind of like an iterator to advance to the next key value, returns a true or false value if it actually is data or not. Return the key, return the value, get the progress overall on the file used for the job tracker for metrics to kind of report back, and then finally close the record reader. So in here, you're taking that input split and you're like, reading byte by byte or however you feel like to read in that line of text. Mapper, this is a class that is often extended to do anything. There's a setup and a cleanup method to do any preliminary processing, opening up reference data, loading it into memory, anything like that. A cleanup to close up anything. The map function, this is called the identity mapper, which just takes the input key and input value, converts them to the output data types, and writes them out. As well as a run function, you can see set up, while that record reader has values, get the key, get the value, and pass in this context object. And context is basically like configuration used to write out output and things. So you extend this class to do any type of processing that you want. The partitioner is part of that reduce phase of where does this key value pair belong? What reduce task does it go to? It gives you the key, the value, and the number of partitions, which is essentially the number of reducers that you're going to have. If you have 10, you're basically going to take this key value pair and make sure that the keys that are the same value end up at the same reducer host. The default is a hash partitioner, which uses the key's hash code mod number of partitions. So you'll get a number from 0 to 9 in the sense of 10, anything like that. So since that key's hash code, the same object's supposed to have the same hash code, so they'll end up at the same reducer. So now there's all the shuffling and sorting happen. That's managed by the partitioner. The reducers copy everything over. Another class here, setup cleanup. Reduce, it gets this key and an iterable over all those value types. So this is going to be the word and then basically a bunch of numbers, a list of ones, say. And run is pretty much the same there. Output format, get record writer, check output specs, which is just to make sure that you can run in the sense of Hadoop. It doesn't want to clobber its own output directory, so it will check that the output directory does not already exist. There's also an output committer, which you don't really need to worry about. It's basically, if the task fails, it'll clean up anything that it wrote out already. And the record writer, very simple interface, write, or abstract class, I should say, write out the key value and close the file. So let's kind of look at what this actually is in the word count sense. So for some very basic MapReduce, yeah?
These always spin up from scratch, like a Java main, or can you have files running and avoid the initialization process?
Short answer is no, you cannot. So it uses, like all these pieces that I'm talking about, like they're configured in that job manifest with your jar file. So when a task tracker gets it, it looks at that configuration and uses reflection to create these classes on the fly as it needs them, yeah. So the problem here, we want to count the number of times each word is used inside a body of text. And we're going to use the text input format and text output format, which have corresponding line record readers and line record writers. So a lot of pieces that were already written by the Hadoop framework, by the Hadoop API. There it has the default hash partitioner, a lot of pieces like that. So for our map, we're going to get a byte offset and a line of text. For each word in that line, we're going to write out the word and the number of 1. For reduce, we're going to get a word and a list of those counts. And we're just going to go through that and sum up all of them and output the word with the sum. So we need to write some mapper code to do that. So this mapper is templated to long writable text. Those are the input key value pair data types. And text int writable is our output key value pair data types. So for map, we're going to get the long writable, which is the byte offset, and the text is the line. We're going to take that line, run it through a string tokenizer utility to basically chop it up into words. So while there's still more tokens there, we're going to set our output key, which is word, to that word and context.write word with the number 1. And the 1 is just this int writable static object. So we take that line of text. We don't know where it came from. We don't know what host it's on. We don't know anything about that. We're just operating on a line of text, iterating through it and outputting each word with the number 1. Next up is the shuffle and sort, which in the interest of time, I will breeze over. So each mapper writes out a single file that is logically partitioned by that partitioner. I have 4 reduce tasks I get 1 from 0 to 3, 0, 1, 2, 3, each piece of that. Reducer copies each one of their pieces from all of these mappers. 0, 0, 0, 0 goes to reduce 0. It sorts these partitions, basically using a merge sort algorithm, into one specific file, and then that's read in by the reducer. Very complex thing. It goes into detail in Tom White's Hadoop, the Definitive Guide, if you really want to know about it. So taking a look at the reducer code with that, I'm going to get the key, which is going to be unique across the system, and an iterable of these ones, essentially. So for each one of these values, we're going to get that int and add it up to the sum. We're going to set our output value to that sum, output the key with that output value. That's word count. You all are now Hadoop pros. So what is so hard about that? The problem is all of these problems that you're going to have in working with MapReduce need to fit in this really tiny box called MapReduce. It's very much a limitation. It's kind of not like a feature, I guess. It's a really new way of thinking about this. So simple processing operations that we're used to, like joins, are not very easy when expressed in MapReduce. There's like 4 different types of joins, so you need to take into account how much data am I processing, which type of join do I want to use. Cross products are a whole other story. The proper implementation piece is not so easy to do that. There's a lot of configuration variables, implementation details. How many reduce tasks am I going to have? Is my data skewed for these key groups that I'm creating? Is one reducer going to have too much data to operate on? I've got to worry about JVM size. I've got to worry about garbage collection. Like a lot of different things to come into play with that. So Hadoop is primarily written in Java. All these components are extendable, configurable. Custom I/O pieces through input and output formats. You can create custom formats. You can read and write to external systems that you have. There's a lot of higher level tools out there to enable rapid development. Pig, Hive, SQL on Hadoop. The Spring for Apache Hadoop framework also helps simplify this development effort. So don't be totally scared away. It's not that bad. Hadoop.apache.org is the website. It's an extremely supportive community. When I first got started, I joined their user email list and just absorbed information like a sponge. That's what I do. Strata and Hadoop World, October 28th through 30th. We'll be in Manhattan this year. If you feel like going, I'll be there. You can come say hi. There are lots of resources about their blogs, email lists, books. If you want to know design patterns for MapReduce, somebody named Adam Shook wrote a book on it. My friend Don Miner. So this book, we kind of went through how do I implement distinct? How do I implement joins? Kind of taking the piece of how do we kind of do this data processing analysis and express them in MapReduce. This wasn't anything new that we spawned up out of our head. A lot of this information was out there already. We just kind of collaborated it together. We do have a website, mapreducepatterns.com, that has nothing on it. So if you want to bug me about it, maybe I'll actually put stuff on there. Our intent is kind of open source the material in there a little bit. So there's that book. As far as getting started is concerned, Pivotal, we have a single node VM that you can download directly from our website that has Pivotal HD installed on it. It's consisting of HDFS, MapReduce, Pig, Hive, Zookeeper, HBase, HAWQ, Mahout, Flume, Scoop, pretty much everything that I've been talking about here is in that single node VM for you to just start playing around with. We also have a community edition you can download. It's our distribution of Hadoop. That you can download and use on actual clusters if you feel like. For the brave and bold, you can roll your own. If you just feel like downloading stuff from Apache, you can go check out the docs on hadoop.apache.org. Download everything there. Obligatory acknowledgement slide. Yeah. I would happily give you my Twitter handle. It's @AdamJShook, but I don't use it that much. But I know people like Twitter. Are there any? We have about 4 minutes or so on my clock. So if anybody has any questions, or want me to kind of go over stuff, I know this was a huge amount of information to throw at you. I hope you've gotten something out of it, feel free to email. Yes?
You mentioned some ideas. Is there any like Cloud Foundry simple things that we can deploy?
I heard, I guess yesterday, that they've put Pivotal HD distribution on Cloud Foundry. I don't know a lot of the details behind it, but they're working on that. They're working on putting it in AWS also. Yeah. Thank you.